Hi everyone. So welcome to the 12th and final week of our NPTEL course. So before I begin, I would first like to know whether you got the announcement for the extra lecture. Can someone confirm?
Give me a minute. I'm checking the announcements.
Okay.
No, there are no announcements for the extra lecture.
Okay. If there are no announcements, then I think it stands cancelled. I don't know what happened. They haven't informed me either. So, okay. So this is the last lecture. And there is a slight change in the outlook. I hope you do not mind. So, as usual, we'll start with a recap and then we'll look at the problems. So, we started by noting down the Hamiltonian's or canonical equation of motion, which is q dot is equal to derivative of h with respect to p, small p, and p dot is derivative with respect to small q with a negative sign, right? And you can do it for each degree of freedom. So if you have n degrees of freedom, you have two n equations. All of them are first order, and q and p are treated on equal footing, right? And which will become important when we do canonical transformation. So then we tried to figure out if given some general function f, which is function of q, p, and t, its time derivative f dot, that would look something like this: Poisson bracket of f with respect with h and plus whatever the explicit time dependence there is. Okay, and this is defined as with respect to q, with respect to p, minus with respect to q, with respect to p. So first f and h, then h and f. Okay, so this is the definition of Poisson bracket of two functions. So in our case, this f is the first function and h is the second function. But in principle, it could be anything. And why is it important? Because when we take time derivative, it naturally appears. Okay, so this means if f is constant or integral of motion, then f dot is 0, which means this Poisson bracket is equal to minus partial of f with respect to t, right? Okay, and if f has no explicit time dependence, explicit t dependence, then clearly the term on the right hand side is 0. So this Poisson bracket must be equal to 0, right? So this can be used as a test whether f is integral of motion if it doesn't have time dependence. Okay. Then the next thing was properties of Poisson brackets. The first was antisymmetric, very easy to see. If you switch the order, you pick up a negative sign. The second one was if you take Poisson bracket of any function with a constant function, this is equal to 0. Why? Because we know that derivative of a constant function is given by c with h. So at least for h, it's obvious that it is 0. But you can do the calculation. In both the cases, you have derivative of c, right, in both the terms. So it should be 0. Okay. The third one is linearity or linear superposition. This is if you have f uh, and the second function is superposition of two functions or linear combination, then resultant is just c1 times fg1 plus c2 times f with g2. Okay. Then fourth is product rule. If you have two functions Poisson bracketed with h, then you have f times gh and g times fh. So if you realize, if you have done quantum mechanics, all of these properties have equivalent property in quantum mechanics as well. You just replace your Poisson bracket with your square bracket. Then the time derivative of fg is again similar to the product rule, plus f with time derivative of g. Okay. And this Jacobi's identity, which is that if you have f, g and h, three of them, and if you permute cyclically, so now bring h here, push f to the right and push g to the right. So now h, f and g, and do again same thing. Bring g to the first place, push h and f to the right. So you have g, h and f. This must be 0. Okay. Then if you take Poisson bracket of a function with qk, you get the derivative of that function with pk. Okay. And same for p, you get derivative with respect to qk. Okay. And the last one was uh, so-called Poisson's theorem, which says if f and g are integral of motion, you can find another integral of motion, which is just Poisson bracket of those two, that may or may not be, by the way, independent of f and g. So you may find a new integral or may be dependent on f or g. But nevertheless, this resultant function would be an integral of motion. Okay. So then we started looking at canonical transformation, and the idea was that for canonical transformation, idea was that the Hamiltonian equations or even Lagrangian equations are derived from the concept that the difference in the or difference should be difference of this LDT, which is the action, should not change at the extremum, and that is where your physics happens. That is where your equations of motions hold true. Okay, so and L can be written as P q dot minus H, right? And this is equal to 0. What this means is that if we have PQ dot minus H, and if we have another set of variables, capital P, capital Q, and H prime, they can at most differ by some total derivative, right? Why? Because boundary points are fixed in our formulation. Okay, so the df becomes pk. Let me just remove index k from now on, minus p dq plus h prime minus h dt, right? So f is called generating function. What does it generate? It generates a transformation that is canonical, and canonical transformation is such that even in the new system, after being transformed, it still respects the Hamiltonian or canonical equation. Okay, so and from this one we can derive P and Q in terms of older ones. So small p would be derivative of f with respect to q, and capital P would be derivative of f with respect to capital Q with a negative sign, right? Just these coefficients. Okay, so this was our first kind. Later on, we can use the d of pq is p dq plus q dp, and same for the new variable capital P and q, p times dq plus q times dp. So if you realize, we have this kind of p dq term here, so we can replace this term by adding this total derivative minus this thing, okay, etc. So when you do that, you can have three other kind of generating function. The second kind is f2, which is a function of old q and new p, in which del f2 by del q is small p, and del f2 by del capital P is capital Q. Okay, then you have third one, in which del f3 or del small p is equal to minus q, and del f3 with no q is minus p. So this f3 would be function of small p and capital Q, right? So the first one is always old one, this is new one. So of 3, f4 would be a function of small p and capital P, in which f4 with p is small q, and with respect to capital P it is capital Q. Okay, so there you have it, all the four kinds of generating functions. And the good thing is that this could be any functions that can just take these inputs and you get a new transformation that is guaranteed to be canonical. It may be trivial or it may not be trivial, but it always generates a transformation. Okay, so in class we saw the very, what should I say, trivial and easy examples, which is F1 is just given by Q times capital Q. In that case, Q becomes P and sorry, small p, and new P becomes minus small q, old one. Okay. Oh, so by the way, any f should have one old variable and one new one, right? So the old could be small p or small q, new one could be p or q. So you have 2 into 2 combinations, and that's why we are getting four kinds of generating functions. Okay, four kinds. Okay, and the fourth one, which is small p times capital P, also generates the same thing, in which you are interchanging the variables. So your momentum becomes the coordinate and coordinate becomes momentum, but with a negative sign in the momentum definition. Okay, and F2 given by QP and F3 given by minus PQ both generate identity transformation, which in simple language means do nothing. Q stays Q and P stays P. Okay, so identity transformation. And as we saw, for multiple degrees of freedom, you can have mixed transformations also, in which for some of the degrees you have first kind, for other degrees you have other kinds, etc. Okay, and so after that, we saw an example of harmonic oscillator. And if you are a physics student, one thing you definitely know is the Hamiltonian for a harmonic oscillator, which is this, right? And you can take out 2m so that it becomes 1 by 2m p square plus m square omega square q square. Okay, and what we want to do is just write this as some capital P. Okay, and that is our kind of goal, so that the q does not appear. This is some function of P. So what we want to do is have small p, which is some function of capital P times cosine of q, because we realize that if this is something times cosine of q square, and this is the same thing times sine q square, then that cosine square plus sine square would give 1, and there won't be any q. Okay, so small q is same function of p with sine q. Okay, rather m omega q, because we want to take out f of p common. Okay, so when you do the algebra, I don't want to repeat the entire thing, but at the end you get f of p as square root of 2p by m omega. Okay, and in that case h prime, which is just the h written in terms of new capital P and Q, is just omega times p, right? And then we can use equation of motion, which is del S prime by del p is equal to q dot, that is just omega, which means q is equal to omega t plus phi, where phi is some initial phase. Let me call it phi naught. Okay, and that means q, which was defined through this relation, is square root of 2e by m omega square sine omega t plus phi. So you see, we never solved the pendulum equation or anything. We just used this Hamiltonian, found a canonical transformation in which q is cyclic, and from that we got our solution, our original q as a function of t, right? We never appealed to Newton's laws of motion, we never took the cosine component, we never cared about the tension force, etc., right? Of course all of those things was absorbed in this Hamiltonian, but this just goes on to show the beauty of it. Okay, and the last thing which we did was with Poisson bracket, and so one thing you can notice is that Qj with Qk should give 0. I think professor has mentioned it as delta Jk, but I think it's incorrect, or maybe I'm mistaken. I don't know. And same with momentum, right? This is 0, but Qj with Pk would be delta Jk. And this should ring a bell. If you have done quantum mechanics, you know that if you take two operators x and y, the commutator is 0. Okay, x and x is also 0. Px and py is also 0. Px and px is of course 0. The only way to get a non-zero component is have different, let me change the order, x and px, right? And this gives some non-zero value. I think it is IH cross. I might be missing a factor of I or minus 1. But so the same way, if you want to get a non-zero Poisson's bracket, you should have Q here and P here. That is one thing. And you should have same index J and K here, right? Otherwise, this would be 0. Okay. And the last thing which we studied was theorem of Poisson, which is that uh, for us it's a
I
test.
have a question there.
Yeah.
So in quantum mechanics, when we evaluate the commutator relations, they tell us whether two operators are, whether two operators can be measured simultaneously or not, correct?
Uh-huh.
So if
Yeah.
they don't commute, we cannot measure them simultaneously. So
Right.
is there any similar concept here in Poisson bracket? So if there is a non-zero Poisson bracket, so
Uh,
what
uh,
does that tell us about the two variables then?
I really don't know. I don't know. In classical mechanics, there is nothing like measurement paradox or anything,
Yeah.
right? But I know that the way to quantum mechanics, in fact, this is how you go from classical mechanics to quantum mechanics. The
Okay.
Poisson brackets become your um, commutators. And if you have done quantum field theory, the commutation relations essentially define your theory, right? Along with the
Right.
Lagrange. Yeah. So, but
Okay.
to answer your question, I don't really know. There might be some deep connection. If I find it out, I'll let you know through email.
Okay. Sure. Sure.
Okay? Yeah.
Okay.
So the last thing, which was this theorem, for us it's a test whether given transformation is canonical or not. And the statement is, if PQ going to some new PQ is canonical, I should write, right, canonical, then the Poisson bracket of PQ under the new variable PQ should also be 1, and in the same way for Poisson bracket of new variables under the old variables small pq should be 1. Oh, I wrote it the other way. Okay, maybe I should put minus sign there. Okay, so and if we saw two examples from the harmonic oscillators. You can check for both old with respect to new and new with respect to old. Both of them give 1, and which means that was indeed the canonical transformation. In fact, the questions that we are going to do also concern with this. So let's look at the first question, which says a transformation is given in which the new capital Q is small p plus I small q, and capital P is alpha times p minus iq, is canonical if alpha is equal to what? So again, if we know that for new Poisson bracket, the Poisson bracket of new q and new p with respect to old q and p should be 1, right? Which means derivative of q with respect to q and p with respect to p minus q with respect to p and p with respect to q. This should be 1. Now let's just put the expression. So capital Q is p plus iq. So with respect to q, it's just I, and derivative of capital P with respect to small p is alpha. Okay, minus derivative of capital Q with respect to small p, which is just 1, and new p with respect to small q, which is minus I alpha. This thing should be equal to 1. So I alpha plus I alpha. So 2I alpha is equal to 1. So alpha is equal to 1 over 2I, or minus I over 2, right? Because 1 over I is minus I. So there you have it. Alpha is minus I over 2. Okay, these kinds of questions often appear in GATE and what is the other? NET. Yeah, those kinds of exams. They tend to ask this type of similar easy questions. Okay, the second one also is on the same thing. The new q is p divided by q, and new capital P is a times q square. So again we use the same thing. Let me just copy this, copy. Okay, so derivative of capital Q with respect to small q is p, uh, sorry, minus p over q square, and capital P with respect to small p is just 0. Capital Q with respect to small p, that is 1 over q, and capital P with respect to small q, that is 2a q, right? And this whole thing should be equal to 1. So this is 0. This q's get cancelled. So you have 2a minus 2a is equal to 1. So a is equal to minus half. Okay. So that's your answer. So both of them tell you the same thing. This is a way to again find canonical transformations without generating functions. You just try to guess the form and see if it works out. So what you could have done was just try q is equal to p by q and capital P is equal to q square, and then you would find that it doesn't work out. So what's the next step? Next step is to introduce a factor somewhere. Okay, here small a, and now see that for some a it works out. Now, it's not necessarily true that there must be some A for which the transformation becomes canonical. For example, you see here it's 0. Here Q's and Q's got cancelled. If they didn't get cancelled, then no matter what the value of A is, this equation can never be identically equal to 1, right? Because it depends on Q. So you have to get rid of P and Q in this commutation, or rather the Poisson bracket. Okay, but this is one of the ways in which you can find out. Here also we had a factor of alpha, and once you know the alpha, then you have the canonical transformation. Okay, so yeah, so the third and fourth question, which were there in the assignment, are the same as the ones which we discussed last time. So no point repeating them. You can see them on YouTube in week 11. So this is from week 11. I don't know why are they repeating. I will write to them. And yeah, so that kind of concludes our discussion. If you guys have any questions, remarks, anything, any doubt in the solution. Okay, so we have four people with us. So let me just thank you, all of them, especially the ones who are attending the live sessions and all of them who are watching on YouTube. I'm sure you enjoyed learning this course. I most certainly did. Yeah,
Hello.
yes,
Yeah, I have one doubt.
sure.
If the canonical transformation, the
Mm-hmm.
Poisson ratio is equal to 1, if
Mm-hmm.
suppose P or Q is in that equation, then how I solve this equation, then find the alpha value?
Okay, let me go to the problem. Uh, so let's look at the first one. Are you seeing the screen?
Yes.
Yes, sir.
Yeah. So in the first one, uh, do I have a laser or something? Okay. Anyways, so this equation must be true always, right? If the transformation is canonical. For this particular given transformation, which is some transformation as a function of alpha, right? We can have any alpha. And what we want to do is find out the precise value of alpha for which this transformation becomes canonical. So we are calculating for every alpha what is the value of the the commutation, the Poisson bracket, right? And that value is 2I times alpha, and that must be equal to 1 for canonical transformation. So from this we can get the value of alpha, which is 1 over 2I in this case. So do you understand it now?
No, sir, I ask like that. If suppose 2I alpha and multiple of P or Q something is equal
Yeah,
to 1, then
yeah.
how I find
Oh,
the
oh,
alpha?
I see. It's a very good question. So the question is, if we got the commutator basically as this, then what does it mean? It means there exists no alpha for which transformation is canonical. Because you see, in principle, any Poisson bracket is a function of P and Q, but for a canonical transformation, it is equal to 1, which is not function of P and Q. So if we get something like this, and we cannot say just alpha is equal to 1 over 2 IP, that would be wrong because value of P changes depending upon where you are in phase space. So and you cannot, and we have treated alpha as constant in deriving this, right? When we say derivative of capital P with respect to small p is alpha, we are assuming that alpha is a constant. So this means this equation cannot be solved by any constant alpha, which means there is no canonical transformation for any value of alpha. Does that clear your doubt?
Yeah, yes, sir. Yes, sir. Thank you, sir.
Okay. Yeah. Sure. Okay. Anybody else?
Good evening, sir. I want to give my feedback.
Sure, please do.
I'm Dr. Meenakshi, working as a assistant professor, associate professor in an arts and science college.
Okay.
So I did my MSc, completed my MSc in 94. So
Mm-hmm.
my age is nearly 50 plus 52.
Wow, that is
So
really admirable. Yeah.
14 years, I'm a pure homemaker.
Oh, I see.
Now I am doing 3 courses in NPTEL, but I am watching the your class regularly.
Yes, yes, I've seen, I see your name every week. So
Very much
uh,
interested, very excellently you are teaching. So
thank you.
today I felt that I'm going to miss your classes. So I would
Oh,
like to uh, go to my MSc classes.
oh,
So
thank you very
very
much. Your words mean a lot to me. You know, I am just starting my career as a teacher
okay.
and researcher. So
Wish you all the best.
thank you very much.
Keep rocking in your careers.
Sure, thank you, ma'am.
Thank you, sir. Thank you.
Yeah. Okay. So
Hey, Yash,
yeah.
same goes for me. Um, I am a doctoral candidate here at Clemson University, so I join your
Mhm.
courses from the US. So it's early morning, 8 o'clock now,
Oh,
and
I
it's
see.
chilly outside. Okay, yeah.
Oh,
Uh,
wow.
so uh, it was nice. I'm not writing the exam because of the restrictions that my university has, but it has been a good experience revising the concepts
Okay.
for
Yeah.
Lagrangian mechanics. And
Nice.
yeah, thank you very much for the uh, live sessions
Sure.
that helped a
Sure.
lot.
No, I mean the sessions help me also a lot, so it's a two-way interaction, and I really enjoyed your company during the sessions. Thank you very much. Okay, then on that positive note, I think it's time for us to say goodbye. Let me just give the email ID. It's arstotalia at iitb.ac.in. Okay, it's in the chat box. Okay. Okay, so everyone, uh, goodbye and all the best, all the very best for your future endeavors. Bye bye.